Hi, I'm Jose Abel, a civil engineer, and this is a quick video for my finite element students at Universidad Los Andes in Chile, and to whomever else might benefit from it. So today what we're going to be doing is learning how to interact with Gmsh meshes from Python. This is very useful for building finite element code that we can then use with Gmsh to do finite element analysis. So I'm going to start with a model of a dome that I have here. This is a model of a little dome that if I turn the geometry aspect of the surface to be solid, you can see it's a dome with a hole. And then if I mesh this, you can see that we can generate a nice structured mesh for this dome, composed of triangles. So we want to be able to read this mesh from Gmsh to create finite elements and solve some problem. Okay, so I'm going to make sure I save this. It's going to get saved as homework1 underscore structure.msh, and I'm going to be reading this file here from Gmsh. So we import the Gmsh library, and I'm importing NumPy because I'm going to be using that later. We'd have to initialize Gmsh, then we open the file that we're interested in, and we always need to finalize Gmsh so that it does some memory cleanup. That's a good idea to do. And when you issue this gmsh.fltk.run, it's going to bring up the Gmsh GUI. So let me execute the script real quick. And you can see it's just the mesh. There's no geometry here. So it's just the elements that have been meshed. If I want to remesh, I would need to do something else, manipulate the geometry. But I'm just loading the MSH file here. I'm going to leave this commented for now. So now what we want to do when we build a finite element code is we want to be able to take this mesh. This MSH file, by the way, it's a large text file that has some structure. But since we have a Python API to be able to read this file, we're not going to be focused on the structure of this file. Anyway, so we want to get the nodes first, and then the elements, and then with the nodes and the elements, build a stiffness matrix, apply boundary conditions, and all of that. For this example, I'm just going to be computing the surface area of the dome. Now here we have our first function that we're going to be using, and we're going to make sense of it in a while. So we're going to be using the getNodes function. Now to see all the functions that are defined in Gmsh, we actually want to take a look at the documentation. So getNodes, we're going to take a look in here in the official documentation what the getNodes function does. So you can see here that it has some inputs, some out, and produces some outputs. Okay, so the first input, this dim parameter over here, is as this says, is classified as an entity dimension. So all geometric entities have a dimension. They're one. It's 1 if it's a line or a curve, and it's 2 if it's a surface, 3 if it's a volume. So in this case, this doesn't matter too much. We're going to supply -1 to just say that we want all of the dimensions, and if we supply a tag of -1, we're going to get all of the nodes. Otherwise, we can specify, I want node 10, so you'd supply that. So once you run this, you can see that if we print the node tags and the coordinates, what you get is a list of node tags, that means node numbers, and then the coordinates that correspond to those nodes. Now the coordinates are specified as a vector. So what I want to do is I want to reshape that into a matrix so that I can make more sense of this. So reshape, we call the reshape function with a -1 so that it figures out what the number of nodes are by 3, and now I get a nice array of coordinates. And I can use that array to take a look actually at on a node by node basis what the numbers and the coordinates are. So I can do a nice for loop here to print the node number and the element or the node coordinates. There we go. So we have an array of nodes, node coordinates. Now this array is 0 based, and you can see here that the first tag is 1. So we need to keep that in mind when we access the XYZ array in the future. And then next thing we want to do is we want to get the elements, and for that we're going to be getting elements by types. But before that, we need to see what types have been defined in the domain. There's this handy getElementTypes function that lets me know what types of elements have been defined in the mesh, and when I execute that, you can see that we have elements of types 1, 2, and 15 defined in this mesh. Now, what are the element types? If you go into the documentation and you go to the part of the documentation where you have the mesh file format, right at the end of this section, you'll see what the element type numbers mean. So type of number 1 means a 2-node line, so we have several lines. And a type 2 is a 3-node triangle. And this type 15 is actually a 1-node point. So we have some points defined in our domain. You can see them when you execute the script as these points over here. So we're going to just be paying attention to the triangles. Let me comment this part out. So we're going to be calling this function called getElementsByType. It takes as an input, you can look it up also in the documentation, getElementsByType, to see what the documentation says about it. We're going to be accessing triangles, and we're going to be requesting all of them. You can select them by type too if you want so, but that's all we're going to be supplying this function as an input argument. And it's going to give us out the LA tags and the node tags arrays. Let's print those out. So as before, we get a vector of element tags, and then we get node tags. Each of these elements, we know it's a triangle, so it's going to have 3 nodes per triangle. So this is something I can also reshape so that I get per each element tag I get 3 node numbers, and I can use that information then to actually take a look at what the tags and the element numbers are. So for this for loop, I'm getting element tags from the LA tags vector and the node tags from the node tags array, and I'm just reporting that each element has the following node tags. So now the final thing we want to do is we want to use this information to compute the surface area of the dome. So I'm going to create a variable called surface area, set it up to be 0, and then I'm going to accumulate on that variable the differential area of each triangle element. So just before doing that, I'm just going to iterate over each of these elements that I have here, and for each of them I'm going to compute the area, and I'm going to add all those areas of all those little triangles up to the complete surface area, which will approximate the surface area of the complete dome. So for that, I have the surface area. I'm going to be accumulating a differential area. I'm going to call it dA for each triangle, and we're going to be computing the differential area using Heron's formula. So Heron's formula for a triangle area. So that formula is the square root of the semi-perimeter, S minus A, S minus B, S minus C. That's the formula I want to use, where A, B, and C are the sides of the triangle, the side lengths of the triangle, and S is the semi-perimeter. So that means A plus B plus C divided by 2. So we need to get the lengths of the sides of the triangle, and I'm going to get that information from the coordinates that I have stored and the node tags that I know for each element. So for each element, its I node, its first node is going to be X, Y, Z, and I need to use the element, the node tag. So the node tag for the first is going to be nodes, the nodes array at 0. So for example, this node, this element 1222, its first node, its I node is 117. So that's my first component in the nodes array, and I get all the values. So this is going to have the XYZ coordinates of the ith node of each element. And I repeat this process for the J node and the K node, 1 and 2. Now I need to be careful because these are 1-based indices, and I need to turn them into 0-based indices by subtracting 1. Now when I execute this, I'm going to get an error, and that's because these are not directly integers, what I'm getting out of Gmsh, so I need to convert them to standard integers so that I can do indexing with them. That's a little nuance here, but that's the only issue. That's the only strange part of using this. Okay, so now I have the xi's. I'm gonna, now the error I'm getting is with this perimeter formula because I haven't defined any of the things. So I'm gonna comment it out. And before doing anything else, I'm just gonna inform quickly where the node locations are so that we can take a look and see that we're actually doing everything right, like this. So we can see now we get a printout of xi, xj, and xk positions for the ijk nodes of each element. Okay, let's silence this. But we can use that information to compute the sides. So for that, I'm going to use the numpy dot function, and I'm going to dot xi minus xj, xi minus xj, and that's going to give me the, if I take the square root of that, the length of a first side, and I'm going to repeat that and say b is with the kth node, and otherwise is the kth node with the jth node, like this, and that's going to be our c side. And once we're done with that, we can compute the total surface area, and we can report. So print out f total surface area is going to be surface area. So that whole process gave us a total surface area of 2,425 units squared, whatever units we're working on. And actually Gmsh gives you a way to confirm that. In here you have a plugin you can run, and that plugin is called something volume, mesh volume, and you can give it a dimension here, so it's a dimension 2 volume. If you run that, it's gonna report in a kind of a funky way, but it's this color bar here that is 2.43 times 10 to the 3. That's the same number essentially we're getting in our script, 2 point something times 10 to the 3. So that kind of confirms that we are correct in what we're computing here with Python. So this gives you an idea of how to use Gmsh and Python together to come up with a script to do something interesting. The next thing is to, with the number of nodes, you can start sizing a stiffness matrix, and then you can assemble elements in a loop that looks kind of like this. This is actually an assembly process. We're just assembling the area. We're not assembling a stiffness matrix, but we have all the information we need to assemble an element if we want it. And then from that point, you can do your solution, and with that you can visualize displacements back in Gmsh. I'm going to teach you in another video how to do that. Anyway, that reaches the end of the video. If you like this content, please like, subscribe, and if you think this will be useful to someone else, please share it wherever you think that's relevant. Until next time, see you later.